Welcome everyone to another session of the AI Research Bites. This short series of short and informative talks showcase cutting-edge research work from ServiceNow's AI research team. The AI Research Bites are open to everyone, especially those interested in keeping up with the fast-paced AI research community. Our audiences are AI practitioners and PMs working on AI products. As always, we will have a short Q&A at the end of this presentation, so keep up until the end. Today's session features Étienne, features Étienne Marcotte, who's an applied research scientist at ServiceNow. He has a postdoc in operations research from Université Libre de Bruxelles, as well as a PhD in physics from Princeton University. His current research includes time series forecasting and retrieval augmented generation, both using machine learning. Up to you, Étienne.
So thanks for being here with me. I will present TACTiS, which is a forecasting model, which I co-developed with Alexandre Drouin, Arjun Ashok, Valentin Zandelegui, and Nicolas Chapados. So to start, a quick safe harbor notice. This is current research, so everything presented here is as accurate as our current knowledge. So first, what is forecasting? And in particular, what is multivariate probabilistic forecasting? And why do we care about it here in ServiceNow? So first, what is multivariate probabilistic forecasting? So let's presume you have some data generating process. So for example, CPU usage in data centers. So you have multiple different variables that together move with time. So our goal is, given some kind of history, so the gray part here in these figures, you want to forecast what is the future, so the shaded part. So if we were to write it in mathematical form, and especially in the card, where we don't want only the average and expected value, but we actually want to know the shape of the possible value in the futures, we want to generate a probability distribution. So we want to get the joint distributions of all of these future variables given the history. Or in machine learning sense, we want to train a model that output the parameter of these distributions given the history and all of the training data that relate to this distribution. So let's go back to a use case that would be relevant for ServiceNow. So let's think of how much CPUs are being used in different data centers all over the world. Well, let's wait a little. Maybe we don't want to answer this question straight away by saying, oh, we need to use this and this method. We need to ask ourselves, why do we want to do this forecast? Because different questions actually require different forecasts. So let's take the first one. Let's say we want to estimate for some reasons the expected power bill for a single data centers or multiple data centers, but want the value individually for each of them. But in that case, we don't need probabilistic forecasting. We don't need multivariate forecasting. We need univariate non-probabilistic forecasting, for which there's many methods. But then let's get a slightly more complex use case. So let's say we want to provision, like add enough CPUs such that any customers that make requests to the data centers are not queuing 90% of the time. Well, in that case, you do need to get the probabilistic versions of the forecast to be able to answer the questions of how many CPUs are needed for this. But let's go even more complicated. Let's say the data centers can actually talk to each other, so any task can be transferred between data centers. Well, in this case, you actually need to go to the multivariate versions of the probabilistic forecast because there's a lot of difference between uncorrelated and a correlated distributions between multiple data centers. So if there are two data centers have a highly correlated demand, then they both peak at the same time, and you need more CPUs than if they are uncorrelated, such that when one of them peak, the other may be mostly free or mostly empty, so you can do load sharing between both of them. But in our case, we're actually interested in being able to answer all three of these questions, but mostly the more complicated one that needs the multivariate and probabilistic forecasting techniques. And so let's talk maybe a little more about the extra requirements we want to add to the model we're currently developing. So first, we want to have non-parametric estimator. The reason is while parametric estimators can work very well, they're limited in what kind of distributions they can output. For example, if you have a Gaussian parametric estimators, they can only output Gaussian distributions, which may not fit the reality of many data process. Second one is we want to get arbitrary prediction task. So forecast time series is not only about forecasting the future. Sometimes we want to do interpolations of missing data in the middle, or sometimes we want to do some data analysis, for example, like anomaly detections, which requires being able to forecast any portion of the data based on any other portion. A third requirement is to be compatible with extra covariates. Covariates are extra useful informations that the practitioner add to the model. So for example, if we know that on a certain date, the software of our data centers has changed in the past or will change in the future, well, that's useful information that the model should be able to take advantage of. Another one requirement is robustness to missing values, because as people that the time series are fully aware of, often when you're generating data, you're looking at your data process. Sometimes you have bugs, sometimes you're missing values, or sometimes it's even more fundamental. Sometimes the data didn't even make sense on a specific date. For example, it's a holiday, there's no such date on that day. So we want a model that can seamlessly ignore all of those issues. In short, we want a highly flexible model. So these were the requirements we're thinking of when we're creating TACTiS. And so why not use pre-existing models? Well, let's mention a few models that existed when TACTiS was being created. So we have DeepAR, which is a probabilistic model, but it's univariate. So again, we cannot do the more complex use case. You have NBITS, which is non-probabilistic. So it can only give average and not give like the range of possible values a variable can take in rare or even less rare scenarios. Third, GPVAR, which is a multivariate probabilistic model like TACTiS, but it does require aligned time series. So if your data process receives data at different time for different series, well, GPVAR cannot work as it goes for aligned case. So now I will introduce the architecture of TACTiS, which is a general purpose multivariate probabilistic forecasting model. So let's first look at its high-level architectures. It's transformer-based with an encoder and a decoder. But one thing of note is that it actually has two independent encoders, one which feeds the marginal part of its decoder and one which feeds the coupler part of the decoder. More on that later. The marginals encode the univariate distribution of the forecast. So it's all of the probabilistic information you need for a single variable. If you ignore everything, you're asking yourself, what's the distributions of the CPU usage of a single data center? That's in the marginals. And you get one marginal for each variable. And the coupler encodes the multivariate dependencies. So if two data centers are correlated, that's a coupler that will tell you that. Or it's also because we treat different time as different variables. If there's a correlation between, let's say, the usage of CPUs at 4 o'clock and the usage of GPU at 5 o'clock at the same data centers, that will again be encoded in the coupler. So this split architecture has some advantage that we can see during training, because instead of training the full model in one go, we can first train the marginal until we converge to the best possible marginals, and then we freeze the marginals and we start to train the coupler. This has some theoretical advantage, but it does speed up the training. So for those that are not familiar, let me quickly mention what is a transformer. And the best way to explain what is a transformer is to mention what happened before transformers. And for sequence models where we're generating either words or time series, people were often using recurrent neural network. And in a recurrent network, you have only interactions of a given value with its preceding values. So if you wanted to forecast, let's say 12 hours in advance with 1 hour increment, you need to do 12 steps. And every time, all of that information you need at the end of your forecast need to have been brought over from step to step. But for transformers, you're allowing yourself to do an interaction between any possible time. So you can directly go 12 hours in the past, look at the information here, and using the attention mechanism, bring back it forward. So this is particularly helpful in time series, where often you have data that is not short range, but long range. For example, if you have a process that have a strong daily seasonality, you can look explicitly for 24 hours in advance, get the information there, bring it forward, and use it, instead of having to get a model that have learned to keep this information for 24 distinct steps. And the other peculiar part of the TACTiS model is the coupler part. So the coupler is a very interesting statistical object used to model the interaction between different variables. So while there's some mathematical properties that I gloss over, I think the best way to talk about the coupler would be to correlate to the correlation matrix. So the coupler is the much more refined correlation matrix that only contains the information of how what happened to one variable influence what will happen to another variable. So are those variables correlated? Well, you'll get a very nice line of the in the coupler, but if they are uncorrelated, then the coupler is going to be uniform. So now, after I've introduced quickly TACTiS, how does it fare? Is it actually good at doing its primary task, which is forecasting? So for that, we actually did a benchmark with a bunch of state-of-the-art models that are also multivariate forecasting time series model. However, this benchmark was done on this very specific task of forecasting with aligned times and with like perfectly clean data with no missing values. So this is only a very restricted range of what TACTiS can do, but this range is actually what the other models are good at. But even then, TACTiS performed admirably and getting in first place, especially the updated version of TACTiS, which we call TACTiS 2. But even with that, TACTiS is pretty robust. So we can see that it can forecast non-trivial distributions. For example, in this case, a distribution with a strictly positive requirement. It's also able to do missing values interpolation, which was not part of the benchmark, and also forecasting irregular time series, again, not part of the benchmark. So what does it mean? Well, it means that TACTiS does get state-of-the-art accuracy. And even then, it's also very flexible. However, I gave you the good part of TACTiS, so let me give you some limitations, because TACTiS is not the God model that can do everything. So what happens if you only have a limited amount of data available? Then TACTiS wouldn't be able to train as many parameters. And so in that case, another model with less parameters, or for example, classical models or other models such as recurrent neural network, will be better suited. Another one that is difficult for most machine learning model is what happens if there's a huge distribution shift that happened very recently. Well, then, since TACTiS have never seen these new distributions, you cannot use it and expect very good results. So in that case, you probably need to add explicit regularization to the model, or wait till you get some values after the distribution shift, such that the model can learn how to cope with it. Finally, what happens if this time and resource are heavily constrained? For example, you cannot train on GPUs, or you want to train in only a few minutes, and you want to be able to do your forecast in a few seconds, then TACTiS is not up for you, because it can take a few days to train and have many minutes to do inference. So what are the next steps? Because this is research, we want to always improve what we're having. So some of them for TACTiS is, first, we want to be able to forecast unseen time series. So to go back to the data center use case, we have a lot of CPU data. So we can train a model to forecast CPU usage. But what happens if now we're introducing GPUs that have a different usage pattern from our customers than CPU? Well, then the model will not be able to reason about it. It won't be able to forecast GPUs data, but we want to add this functionality to TACTiS. And one way would be to add textual metadata by telling explicitly to the model, this series is a GPU with this particular characteristics, and in the past, all the series you've seen were CPUs with this other characteristic. Maybe TACTiS will be able to do this unseen time series forecasting. Another approach will be to create a very good pre-trained model on CPUs, but that is very easily fine-tuned for different domains. So for example, to switch from CPUs to GPUs. So with a very limited amount of GPU data, you can fine-tune the model and then get GPUs forecasting with the same quality you will have gotten with a lot more data. And finally, we want to improve its training and inference time, because the faster it is, the more usable it will be in practice. So thank you for listening to my presentation. And if you have any questions, feel free to ask them. And if you're curious about the TACTiS models, here's our links to both the initial version and the updated version, and the repository containing all of the public code for TACTiS. So thanks again. And if you have any question, feel free to ask.